Okay, well, first, thank you for having me. Thanks to the organizers. I wish I could be there in person. I'll do my best to make this work as well. So I have a fable for rough analysis, especially rough path. And in the spirit of this workshop, we want to look at some anomalous diffusions. So here's my disclaimer. I will show you some things that I know I have done that relates to this topic. Of course, there's always much more. So the two examples I want to start with are very well known. The first one is a Gaussian process, centered Gaussian process known as fractional Brown motion. I think everyone in this audience will know it. The important thing is that you have this scaling property, and of course I could defrost the T and turn it into a dot, so the scaling property holds at the level of processes. But in any case, this is diffusive scaling when H, the so-called Hurst parameter, is 1/2. Otherwise, I guess everyone agrees this will be non-diffusive or anomalous scaling. The second example is the alpha stable process. That's a Levy process, independent increments. So, and that one too has a very nice scaling property. And here it depends on this alpha parameter that has to be between 1 and 2. And you have the similar thing. And you see here, you will never have the correct, H equals 1/2 will never happen here because the scale here is alpha strictly less than 2. So this is per se by construction non-diffusive. So let me make sure I have the screen here. I try to avoid the moving up and down as good as I can. Next one. What are some questions here? Well, many people want to solve or use stochastic differential equations. And when you have a form of this, so this part here would just be an ODE, and then you add your noise part here, and everything can be multivariate. I'm not a big fan of writing out too many indices here, so everything is multidimensional. If this is a Brownian motion, then of course this is a very classical setting. There's a super well-developed theory of strong and big solutions and all that. And the resulting process is even called the diffusion process. So you have the precise scaling that I showed you in the last slide, of course, but at least on small scales, you can somewhat transport the Brownian scaling to the diffusive setting, and you have to twist the definition maybe a little bit to make this precise, but this is still considered diffusive. Now, what happens when you replace your Brownian noise, which is the model case of a diffusion, by something which is somehow non-diffusive? I'm sticking with the two running examples here, and X somehow should stand generically for one of these two. And how do you solve such differential equations? Now, if you're in the Levy setting, Levy processes are special cases of semi-martingales, and the theory of stochastic analysis offers you plenty. In particular, SDEs driven by semi-martingales is a well-developed topic. So you could just say, okay, done deal, I know what to do. On the other hand, you can also leverage the sample pass properties, and I haven't said too much here, but let me go back here. If you know Kolmogorov criterion for the Hölder regularity of processes, then it's immediate from the scaling here that you will have Hölder regularity of exponent anything less than h. Okay. For alpha stable Levy processes, that's not true, of course, because they're jump processes. There is no continuity, leave alone Hölder. What you have to do is switch to p variation, which is, forgiving relative to jumps. And here you have similar results that you have finite p variation. And again, the critical p is exactly the alpha here. And since alpha is less than 2, you can always squeeze it to get p variation with p less than 2. So in short, in this alpha stable world, you're always in a regime that allows you to use what's known as Young integration theory. So this is an integration theory that basically can deal very well with situations when both integrand and integrator are of finite p variation with p less than 2. And so in this Levy setting, you're in there. Just as a cultural remark, the integration theory is 100% due to Young. That's maybe 90 years ago. The ODE case that you need, or the Young ODE case, is actually due to Terry, 30 years ago, I believe. So in any case, there are two regimes here. If you want to use the Young theory, then for Levy processes, you're fine, but for, or alpha stable at least, and for the fractional bound motion case, this is a restriction on the Hurst parameter. You need to basically ensure that your Hurley exponent is greater, strictly greater than 1/2, which amounts to say that H is greater 1/2. In particular, Young does not cover Ito, which is the reason why there is an Ito theory, and it certainly does not cover H less than 1/2. And so this brings us to the next slide. What can you do when H is less than 1/2? And so there's a very old paper, 20 years ago, Kutankian, that understood, well, you have to, so I can't give you a crash course on rough paths here, but in a nutshell, this rough, I'll show you a bit more later in the talk. In a nutshell, you have to construct some iterated integrals, and you do this stochastically in this situation. And if this works and they are nice enough, then you form somehow an enhanced integrating process that you can use to solve it again pathwise in a suitable, higher order ODE type setting that's called rough path differential equation or rough differential equation. Okay, so this construction works. As a physicist, you may just think, okay, let me take my fractional bound motion, let me mollify the sample paths. Now I attach, let's say, this first set or the second iterated integrals, and I can do this certainly when I mollify, because then they are just iterated Celsius integrals, and there's no problem. And it turns out when you send this mollification parameter to 0, then everything converges nicely as you hope, provided your H is greater than 1/4. There's also a threshold by when you pass a third. In this case, you need to attach a third iterated integral, but let's not worry about this. But there's a real problem at H equals 1/4. Before I turn to that situation here, this is still a big success. If you go with this Kutankian construction, and later it was revised by many people, including Victor and myself. If you go with that construction and you construct somehow almost surely a good rough path, then you can just stick it into this rough path ODE machinery and construct a solution to the differential equation by these guys, and everything is nicely quantifiable. So you have continuity results and local expansions. It's a very constructive theory, also with regard to numerical analysis. So this is a very decisive answer, and this has been in my book with Victor. This was explained, and then it was re-explained with updates in the book with Martin Heyer, the second edition from 4 years ago. So this is sort of classical, and there's good material where you can read up all of this if you're interested. And I want to tell you, if you haven't seen it, a little bit update. So when H is less equal 1/4, then already understood by Kutankian, there is no chance to construct a canonical fractional bound motion. Canonically meaning, say, in this Wong-Sakai sense, that you just mollify, do what you do, fingers crossed, you hope it works. Well, if H is 1/4, it doesn't work. So already when you look at the second iterated integrals and you pick out the antisymmetric component that's known as Levy area, and you compute the variance of this guy, then you just realize when you're in this regime here and you remove the mollification parameter, the thing just explodes. The variance of this explodes. So there's no canonical, or Wong-Sakai type construction that works here. So what Terry actually suggested many years ago, I've attended many talks where people were talking about this threshold and what you can't do. And there were papers where people did construct, somehow they made proposals what to do, but none of them was all too convincing, I have to say. And Terry pointed out you should, if the variance explodes, you just hit it with a prefactor that looks at the rate and divide by it. There's a downside to this. If you rescale some of the second iterated integrals multiplicatively, then implicitly you also have to multiply the path itself, the first level, and since the second level explodes and you rescale accordingly, that means your first level disappears, and that has the downside that if you look at the resulting path on the underlying Euclidean space, then it doesn't move anymore. You have rescaled it to a point, which is somehow hard to swallow for some people. In any case, Martin Heyer just carried out this construction, and actually this paper, which is short enough on the archive, has two aspects. One about fractional power motion, which is one of what I'm talking about. And there's a parallel development on the KPC equation, this famous singular SPD he and many have been working on. So let me just inform you that this exists because it fits in this narrative here. This multiplicative renormalization is possible, and it's really this multiplicative that's different to all this previous work where essentially people have a weak type renormalization where maybe you subtract something in the zero Wiener-Ito chaos or maybe in higher ones. But this multiplicative aspect is somehow new and also relevant in SPDs here. And what you get here, which is also conceptually interesting, is you get the weak convergence here to a higher order Brownian rough path. So you start with something which is somehow anomalous as a diffusion with a fractional Brownian motion, but in the weak limit here after renormalization, you end up again with a Brownian noise. So somehow you go from anomalous diffusion back to regular diffusion, but higher order Brownian rough paths are not quite the objects that people would consider as your regular diffusion objects, but they are if you take a sufficiently broad perspective. Okay. Now I should have one more remark relative to my own past on these differential equations driven by Levy processes. So here's our alpha stable Levy processes. And I pointed out earlier that you can solve this equation here in a semi-martingale framework without any problems. And in this case, what is this? If you write it in integral form, this is just a stochastic integral, and L is a special case of a semi-martingale, so no problem, you can do this. And in that case, I should probably be a good person and put the notorious minus here, okay, because this is really in the Ito forward sense. And this should be compared and contrasted to something else, this diamond here. It's reasonably standard notation. It's called the Marcos canonical interpretation. In the older literature, people just talk about Stodanovich, but it's not correct. So there's a reason why people switch to Marcos canonical here. And so here the interpretation is different, and this has nothing to do with rough or non-rough. This is really a modeling question. What do you want to happen when your driving noise here, when there's a jump? What do you want to happen? So if you're interested in modeling in financial mathematics, then the Ito interpretation is exactly what you want. If you're a physicist, then you may think, okay, a jump is just somehow a macroscopic manifestation of a movement that is really very, very fast, but ultimately continuous. And so maybe that the right thing to do is just this macro intuition here. When you have a jump, you just pretend that there's some extra epsilon time that you have available. And in that time here, or so you can make this construction precise. So you open up a little time interval here, and in that time interval, you put in a straight line that goes from where you were before the jump to where you are after the jump. And so that turns your Cadillac path into a continuous path, and in particular on that stretch here, it's a straight line, so it's smooth, and then you solve the corresponding differential equation with that now signal without jumps, and in that time stretch that happens here, you're just solving an ODE basically, and later you want to get rid of this extra time stretch. That just basically you undo this extra parameterization, you close your eyes when this happens, and back you are. And so this is somehow the modeling a la Marcos that is very natural when you think of modifying your noise here. I mean, even when you have jumps, you may modify and get something which is smooth and continuous. And if you pass the limit, then this is then naturally limits will be of this form here. So from a modeling perspective, both serve a purpose, but certainly when you look at limit theorems and also homogenization, this one is the one that is more interesting or more relevant. And let me just point you to a recent paper with my good co-author Ilya Cheverev, Rabanov, and Ian Melbourne, where this was carried out somehow. We had a discrete fast-slow system where it was crucial to have this pathwise Young-Lyons interpretation and not somehow the semi-martingale interpretation. So we could conclude that, there's sufficient suitable conditions, the discrete fast flow system will exactly exhibit this as the effective continuous dynamics. Okay. Now, a few words on multi-scale, as I promised in the introduction. So at this moment here, this is a bit of a sightseeing tour. I hope everyone is okay with this. And I will switch to something more detailed in a minute. The multi-scale situation is, if you go back here, what we've done so far, boom, boom, boom. Here we looked at the Ito equation, just to set the stage, and here we looked at a variation when B is replaced by something else, maybe a fractional Brown motion, and you may have a situation where there are both noises around. There's a B and there's also a BH, or maybe an LA. Let me focus on this one. Let's consider a situation where we have two scales, a diffusive scale and somehow a fractional scale. And let's see, so again, think of X equal as a realization of a fractional Brown motion here, or fractional Brown motion really. And we have these hybrid dynamics, but this first part here, this is just good old Ito, and then we add this extra term here, where again, you have here noise. The assumption here, I mean, you can write down whatever you want at this stage, I'm not giving you a theorem, but let's assume B and BH are independent. So maybe, to put a tilde here so that no one believes that this B and this BH are somehow constructed on the same white noise. And I'm interested in the regime that this BH is really rougher than Brown motion. That means H is less than a half. And for the reasons I mentioned earlier, greater 1/4 is greater than a quarter is needed if you want to be somehow in a well-developed situation where this lifts canonically to a rough path. So I'm not trying to do anything fancy here. So this is in the existing literature well covered, this construction here. But what has not been covered until recently is how you do these things jointly. And there have been various tricks, and I don't want to go into too much detail because that's not the purpose of the talk. But if you put aside some dirty tricks like flow decomposition or doubling of the rough noise, something, there's a good theory to do this where every term really gets, is respected for what it is. And so, for instance, you should not assume that this guy here is, let's say, C2 or C3 regular, because this is just an Ito term that you should be, this should be Lipschitz, and that's that. Whereas here, if you believe in this rough path construction, then naturally it's based on Taylor type expansions. F will need some regularity so that you can, write down the local expansions and get all the sewing type arguments to work on which rough analysis ultimately is built. So this situation is, so I'm jumping ahead down here, there is, again, I believe in my view, a very satisfying theory of this joint multi-scale situation developed. At this, the reference I have in mind here is a paper with Antoine Auquet and Koualet, who is now in the UK. The construction here works for a generic level 2 rough pass. So there's no doubt this could be extended to level 3, but the way it's written at the moment is this a level 2 rough pass. So strictly speaking, when you want to solve this here using existing literature in your next applied project, then maybe you should be safe and make this a third that puts you in the level 2 story and everything is fine. There's another development which at least it fits on the same slide, given the granularity of the discussion here, namely rough volatility. So this has been a hugely successful development in mathematical finance, and it does not come from the rough path community, despite what you might think. It was based on actually work by statisticians and practitioners like Mathieu Rosenbaum, Paris, and Jim Getterall, New York. They observed that if you look at realized variance of or realized returns, and you really look at the time series data, then it's evidence that you're in a non-diffusive setting here. So, and the correct scale here, but there are also two scales. There's one sort of Brown and noise that makes sure that in the end you have a a martingale, like, or at least a semi-martingale, because otherwise you want to stay this world of well-developed finance, of course. But as far as the volatility process is concerned, so you can define this very abstractly for continuous semi-martingales. You look at the quadratic variation, you assume differential characteristics. So the quadratic variation is really, that's a derivative relative to dt on the real line. And that one you call somehow instantaneous variance, and the square root therefore is what you call instantaneous volatility. So that's a stochastic process, and that one doesn't have to be a martingale or semi-martingale for finance to work, because that's not a trade asset. And when we try to understand just under the statistical measure what this instantaneous volatility looks like, they found it looks nothing like a diffusion, but it rather looks like a fractional Brownian motion from the scaling perspective. So everything on small scales doesn't mean it's global in fractional Brownian motion. And so the Hurst parameter that we found, I mean, people are debating this, but it ranges between certainly less than a half. You're certainly in the rough regime. And some people want to take it equal to be zero. You do not, because of the special structure you have in these models, you do not run in this 1/4 problem that is, sometimes it's also misunderstood. So in that sense, it's not 100% the same, but it certainly fits on the same slide. Right. So after all this small talk here, I want to dig into an ongoing project with two good co-authors. I'll mention them in a second, or let me mention them now. Yijian Yuan, who is now in Cambridge with Jason Miller. He was my PhD student in Berlin. And Sebastian Andres, who also has history in Cambridge, but he's now professor in Germany in Braunschweig. So the buzzword here is level Brownian motion. What is level Brownian motion? Let's find out. Okay, sorry, my automatic spelling is on. This was too much of AI here. So about 10 years ago, Nathaniel Beresticki, who was also at the time in Cambridge and somehow a competitor party in Paris, introduced a very intriguing process called level Brownian motion. So that's a two-dimensional diffusion process. It has been generalized to, there are generalizations, but let's stick with the original setup here. Two-dimensional diffusion process, and you should think that it's diffusing in a very rough random environment. And so there's a beautiful picture that I've stolen from a beautiful YouTube video generated by one of Nathaniel's students, Henry Jackson, who I believe was so good in programming that he now works at Google. So there's a beautiful video, you should check it out. So depending on how high you are, when you're very high, then somehow you slow down. When you are down here, you go very fast. So it's a fascinating process here. And as you can imagine, these spikes here, this is a picture humans can see, that in the perfect sense here, these spikes here, it's plus infinity and zero all the time. So it's an extremely rough run environment. And of course, this will kill any diffusive scaling that you may believe in. And so this is even an example of what people call a multifractal process, as opposed to fractional Brownian motion, which is a monofractal. So this is just, if you look at the scaling exponent, right? The scaling exponent in, so if you look at qth moments of increments in the Brownian motion setting, you have a very clear scaling, so Q over 2. And in the fractional scaling situation, you have a scaling of Q times H, H being the Hurst parameter, and these are linear in this exponent. And so these things are called monofractal, and level Brownian motion is actually an example of a process where you have a multifractal behavior, which you can be very explicit about. This is also what's interesting, because you can do something. But anyway, I will not go into that direction. So the question here from the rough analytic perspective is, to what extent do we have a rough pass? So 20 years after, or 25 years after Terry's initial paper, for a stochastic process, being a rough pass is a question that I don't think needs justification anymore. It's one of the key properties of a process. Like, is it a semi-martingale? Is it maybe Gaussian? Is it Markov? The question if it has a rough path left is part of this catalog of things that I feel people should understand when they work with stochastic processes. Because once they do understand it, they can do many more things with it. It's a useful notion. Now, the question, as I posed it to myself, does it have a rough path left? That question actually is despite my speech, is a stupid question, because the answer is mostly yes. There's an abstract nonsense result, which you can also find as exercise in the book with Martin in 2020, second edition, I believe. So I'm not sure it's an exercise in first edition, but who cares? It's in there. You can always construct to a given, let's say, to a given path of finite p variation, let's say p between 2 and 3 for the sake of argument, you can always construct a rough path left. The problem is that this rough path left, so this means a set of second order information that is consistent and placed together with the path itself. That one, you want something canonical about it. If you just make an abstract construction, then you can't work with it. It's not useful. It's just abstract nonsense. I mean, sometimes it's nice to know that this works. Hold on, give me just 1 second, please. Sorry, my roommate just came in. Okay. So, all right, next slide. So to build this process, to make this a bit more precise, I need a bit background, and I know time is ticking, so I'll run on it, and I hope, depending on who you are, you can follow more or less. Stochastic differential geometry. In the end of the day, Liouville-Brown motion is a Brown motion on a very irregular Riemannian manifold, where this G here is, I'll write down a moment, it's just very, very bad. Okay, so before we go in this bad situation, let's think how you do it in a nice situation. And the answer is, well, we're looking to construct the Markov process that has the Laplace-Beltrami operator as a generator. And so you could write it out in local coordinates, solve the martingale problem via eta SCDs. This is, I think people call this the poor man's approach. If you're sophisticated, then you do it following Malliavin, Ellis, Elworthy, and do it somehow in a fancy way on the orthonormal frame bundle, where you can solve it globally as a Stratonovich SDE, because the generator takes some square form, project it down, and it's a beautiful story. There's also the Dirichlet form perspective, where you say, well, we're in a situation, we have a Riemannian manifold, there's a natural notion of a gradient, there's a natural notion of divergence relative to the Riemannian volume form measure. So you can simply write down the quadratic form, so that gives rise to a Dirichlet form, and I've spelled it out here for you. So just get by integration by parts. That's a symmetric situation relative to the volume measure, and that's a Dirichlet form. So now, in particular, you can fire up abstract Dirichlet form theory and construct B as a hand process to this form here with all the pros and cons that this gives you. Okay, I'm not going to. Now, here's background 2, rough paths. So I was talking on and off about it, so let me be a bit more precise. So you have a path, multidimensional, let's say d-dimensional, and what you should try to understand is this set of iterated integrals. So I'm just talking about the level 2 setting here, okay? So this one, you can also think of the integral of dy from S to R. So in that sense, you can also write this as a double integral of dy dy. Everything is multidimensional, so the iterated integrals give you a 2 tensor. Here it is. And if you just try to understand, how do you patch together increments of this? This is not going to be additive because of this minus here. So that's chain relation. But again, I did not plan to give a class mini course here. If the regularity is less, then you may have to attach higher order objects. We don't need this. And this is what I mentioned earlier. When you have, so if y, okay, when does this work? If y is differentiable or continuously differentiable, or y is a semi-martingale, this makes sense. In general, when you just give me a p variation path and we are not in the Young regime, p is greater than 2, then it doesn't work. But maybe someone will come to help, like Ito or Stratonovich. That's great. And in any case, this can guide you in putting down the right axioms. So this is what I mean by Chin here. This will, you just guided by this algebraic form here that gives rise to a certain algebraic axiom that you put in. That's what I said. Now the Wong-Tsakar approach is, I also mentioned this earlier, fingers crossed, mollify. Now everything is well defined. This is well defined, and now you can hope for your best that this converges. Again, that there are counterexample when it doesn't, and we've seen one earlier, this fraction bound motion example when h is less equal 1/4. So even so, it works for many. So there's this naive approach. If you want to prove a theorem, it can be very hard work. It has been shown for many stochastic processes, especially large classes of Markov and Gaussian processes. So also outside semi-martingale. Semi-martingale is like the stochastic calculus world where you know a priori, okay, I know what this means. But there are situations where you didn't know before. And so in the last 20 years, this was all worked out by many people, including myself. Now, let me try here one thing. Let me try to, oops, I'm sorry, share. So there's a tech problem. I will resolve it. Hold on. Presentation mode. Okay. Okay. So this is better. Okay. So background 3, geometric view on rough paths. And I should ask, how much time do I have left? 10, 15 minutes, is that correct? Yes, I'll do my best. So geometric view on rough paths. I think we can skip this. Maybe in a nutshell, if you're interested in situations where a chain rule is persistent, like you come from a Stratonovich perspective, then out of these iterated integrals, only the antisymmetric part matters. That's the Levy area that I also mentioned earlier. And in that case, you have a neat geometric interpretation. So that the process and somehow this Levy area together, they naturally live in a step 2 free nilpotent group, which is the three-dimensional Heisenberg group in case of a planar process, which is actually the relevant case here. And this, so you can identify here it's a Lie algebra, but you can identify it with the group by using the Becker-Capell-Hausdorff formula. And that structure is very convenient because it cleans up these constraints that we said earlier, this chain relation, etc. You can just then talk about path increments in the group, and they automatically do the thing for you. So it's convenience. Algebra can be convenient, and here it's placed together with differential geometry. So we can skip this. Now, Brownian and Markovian rough paths. So if we specialize to d-dimensional Brownian motion, so we are in this geometric setting, then this is what we have, right? The Levy area would be the antisymmetric part of the second level. And then this guy has a name. It's called the Brownian rough path. Okay, so this is some of the plain vanilla Brownian rough path as defined, as has been used for 25 years now. So from a perspective in a Lie group, it's actually has independent stationary increments. So again, it confirms why the group is the right thing to look at. It's also Markov, and it has a nice generator in Hermanda form, namely here it is. And these UIs here are the horizontal vector fields that the generating horizontal vector fields here, okay? It's from a derivative form perspective, you can also define so what is the hypoelliptic gradient? This is just, you look at this, horizontal generating vector U1 up to UD, and then, so here's, you get a d-dimensional vector here. This is just a pairing in RD then. And so everything extends very nicely. So in particular, this brown rough path is a symmetric Markov process. And the derivative form is very clean and very nice. So we have used this to great extent in previous works on Markovian diffusions as rough paths, but I don't want to spend more time with it. So one thing we have to understand is what happens when you have a Markov process, let's say with generator L, and it could be Brown motion, it could be something else. and you want to do a time change here, and more specifically, a time change of this form here. Okay, so what's the goal? You have generator L here, and you would like to, for some reason, to understand the Markov process that has a generator sigma square L, where sigma square is a or sigma is a function in space. So you want to modulate things somehow. And the answer is you can do this very nicely by a time change. And so you have to cook up this F here, and you can read the definition. It's a bit of a calculus, either calculus exercise. And so if you use this F as defined here, and then it's inverse as a time change, the resulting process is Markov. It has this generator. Okay. Fact of life, exercise in stochastic calculus. This gives rise as F to an abstract definition of positive continuous functional. So I don't think I have time to dig in all the details here, but just take it as this type of time change is fits into an abstract concept that is more robust in situations when you can't write this down. So here, for instance, the F would be automatic C1 by definition, and we have situations where it could be increasing, but it just doesn't have to be C1. It could be something like a cantus or something crazy. And in fact, such things are not so crazy when you look at what happens later. The third background, symmetric Markov process, Dirichlet forms. I think we had this. The Brownian rough pass. We had this. So if you look at this example that we had here, so think of A just as the one example that I had here, but it can be more abstract if you want and work with these PCAFs. Then it's a general fact that you can define well, this is just a definition, the so-called Revue's measure. Here it is. So A was this PCAF. This is the process. That's in the so it's an M symmetric. So in our case that we had earlier on our Lie groups, if we work on the Lie algebra, then the Lebesgue measure on the Lie algebra is the left invariant measure, and that is the symmetry relative to this measure. So it's actually quite harmless here. Okay, so that's the Revue's measure, and there are some technical things that it does, and so charging no polar set. And conversely, given an abstract measure, so there's a 1-1 correspondence, given an abstract measure, you can also go back to the PCAF. Okay, let's keep this in mind. We can be very explicit about this in a simple example here. So if I'm in this situation here, I'm writing A instead of F now to emphasize its generality. But in that situation here, that this PCF is really C1 here, the derivative is given by A. Then I can write down this Revue's measure directly by its radial Nikodym density, which is exactly A. So it's very explicit in the regular case, but in general it's still true. So now, how do time changes, how are they reflected? Well, okay, maybe what at first sight it's surprising. If you want to do a time change here, right? There's here it is. B is the process, A is your PCF that you want to do time change with. Then you get a new process B inverse head, that is the time change process. And if you want to understand what is the Dirichlet form of the time change process, you do a computation. It's actually quite funny. You get there's some cancellation here because you have to work with the right measure. You get the same thing. So the Dirichlet form itself algebraically doesn't change. What does change is somehow the domain. So it's really captured in the domain. And you see this here, F is here. Oh. So all this is well known. If you're a specialist on Dirichlet forms, then you know all this. So background 8 is Gaussian fields, because this is the random environment, and there are some pictures that I have shamelessly stolen from the internet, but at least I tried to give some references. I don't have too much time to distinguish all of them, so let's just stick with the Gaussian free fields. Let's say D equals 2. That would be so in D equals 2. That would be one of the interesting things here. So you see what's the definition here? Okay, you have white noise here, and then you transform your white noise using some inverse power of the Laplacian to make it smoother, and then you can quickly figure out what is the regularity of the resulting field here. And the interesting case here is when you get when this regularity here, when this is critical, when this is exactly 0 or 0 minus, then you are somehow already smelling log correlated fields. So this here is one of them is the in the dimension 2 here, d equals 1 would be the Gaussian free field, so it should be this one. Okay. Oh, so Gaussian free field, that's a very famous thing. The GFF Gaussian free field in R2, this is what we are looking at here. And if it doesn't, I mean, you can define it in many ways. What I've given you on the previous slides here, somehow a constructive version built in white noise, but you can also scribble down the correlation function. And what you learn is that somehow it's log correlated. And that means when you look at one point, that's not a well-defined random variable. It would have infinite variance. On the other hand, if you look at 2 points that have some distance here, then it's meaningful to talk about it. And in any case, you can always hit it with test function, and then it makes sense. So it's distribution valued. There's a diagram that I will skip. That a mild complication if you work on R2 rather than a bounded domain that you want to work with the massive field where you choose some P. But again, let me not worry about this. And the important thing now for this construction of Liouville parameter is the Gaussian multiplicative chaos. So this is a story on its own. And so essentially, you start with some Gaussian field. So assume for a moment it's a well-defined Gaussian field and everything makes sense. So h of x is a well-defined Gaussian random variable. And this here is just what some people would call the Wick exponential here. So the expectation of this thing is precisely 1. You have subtracted here whatever it takes to do this, so it's somehow balanced. You can do this in a generality of some ambient measure sigma, but let's not worry about this. We can define this is a random measure, right? So this here is random because h is random, and a here is what you read as a set. So this gives you a random measure. And it turns out you can define this in a meaningful way when h is not a well-defined Gaussian measure, where a Gaussian field where the point evaluation makes sense, but it's only a log correlated Gaussian field. Then it still works, and there are different works. There are important work such as Kahan 85, where he used martingale arguments to prove this, where you do suitable approximations here, you do this big normalization, and then this converges. And okay, there's some non-trivial story about this gamma here. It really makes a difference. So this construction really works when gamma square is less than 2 alpha, where alpha is tied to this measure here. The measure here, needs to satisfy some condition related to alpha, namely this here. Okay, it's a bit technical, but so it's a very non-trivial, subtle theory. Okay? This construction by Kahan was improved by many people, including Nathaniel Bastiki, Vargas, and Kovacs. So now finally, Liouville parallel motion. So we are in this. We have this very nasty or log correlated distribution valued Gaussian field. So it just about fails to allow for point evaluation. And formally, the metric tensor would simply be, so we talked already about time change. So if you think of the Riemannian tensors here, or the heat equation on a Riemannian manifold, that means you just multiply with a scalar to incorporate time change here. And here, what you do here is, this is the time change you want. It's just it's somehow a stretching if you want. The problem is that this here is, is basically the point evaluation is not defined. So this basically is plus infinity or 0 in between all the time. So you have to subtract something really big here. So this is, so coming back to the theme of the workshop, anomalous diffusion, this is certainly not, this will certainly not give rise to some diffusive process. In fact, this is all the interest in the story. So now, Riemannian volume, Liouville measure, etc., etc. Let's not talk about the recent progress in the field here with Jason Miller in Cambridge. You have one of the experts on site here, and the construction so definition, if you want it, that is Liouville Brown motion, is you take a standard Brown motion and then you compose it with this time change f here. And so what is the f? It's the one we had. Basically in, well, okay. It's sorry, what did it say? It's a bit implicit. So you get the measure from Kahan, and this induces PCAF, right? This is this reverse correspondence, and that is your definition of the Level-Brown motion. So we can talk about its nature as a Markov process. There's a derivative form. So as I said, the algebraic is the same as the one for Brown motion because you don't see the time change in the form itself, but only in the domain. And here it is. So mu is the Kahan measure. Now, for the Gaussian multiplicative chaos. So what questions are now, on site, and how do we answer them? So first you sample from your random environment, and then you fix a point, and from that point here you want to start your Level-Brown motion. Can you lift it to a random p-rough path? Again, the simple answer is yes, of course you can. So this is why? The simple answer is, but that's not the interesting one. B is Brown motion is finite p variation. That's effectively not changed when we do a time change. And since X is a time change, you also have locally finite p variation. And then you can appeal to this abstract nonsense result by Lars Victoire that some lift exists and you're done. Okay, so in a sense, it was not a good question. But is there a natural choice for this lift? So I'm just focusing on the area here. And the answer is, well, yes, and yes, you'll see. If there's a natural choice, then that should define what you call a Level-Brown rough path over the classical Level-Brown motion. And there's a simple answer, which is, well, Brown motion is not just any process, it's a martingale. And if you take care of the filtrations, any adapted time change is still a martingale, or at least a local martingale. So Level-Brown motion, as it stands, as defined, is actually a local martingale. So if you're after defining a Levy area, well, just do it using semi-martingale theory, and you can be very explicit about estimating it. There's a whole scale of recent estimates on the p variation of the lifted process in terms of the bracket that you can relate here to the time change. So many things exist from a general semi-martingale rough path perspective that you can simply apply. So, okay, so maybe to make the case here, yeah. Okay. Yeah. Give me 2 minutes to make this, to conclude, thank you. So the first question, yes, and we could answer them quickly because we developed so much tools over the last, X years. So the first really interesting question where you have to understand a little bit more is you want to understand this lift here as a Markov process. Now you can't get away with abstract, special cases of known stuff. And so you need to understand this a bit more and really write down the derivative form, understand it, see how this interacts, the geometry here, both from the level perspective as well as from the legal perspective, and you can do it. Here it is. So let me just say the Wong-Sakai and time change approach. So you can do both. I mean, there's also the naive approach that you take a Level-Brown motion, brutally modify, and then use Wong-Sakai results. So we can do the two, and these two things work and both agree. Let me skip that here. And the last one, which is actually where most of the work goes in with my co-authors now, is so far we have started with Level-Brown motion on R2 and then just edit the area and somehow understand the interplay. But somehow the two-dimensional process lives by itself, and then you top it up. You can make this more intertwined by starting directly with a log correlated field on the group. So now you can create a process on the group here, and if you project it down to the base space, to Euclidean space, it would not be Markov there, let alone any, Level-Brown motion or anything. So in that case, you look at intrinsically a Level-Brown motion on the full group here. And so that, again, we're almost done writing it. This requires a lot of revisiting where a lot of potential theory goes in of basically potential theory on Carnot groups, which is much easier when you do it in a Brown motion case because there it's explicit, and so here a lot things need to come in. And with that, I think I'm done. There's still some philosophical discussion about what the conformal invariance in that case means. We have some hints, but I don't think this is for now. And so thank you very much.
So there is a quick question because we have 5 minutes over time. Please.
Yeah, when you write x times dx, it looks to me a bit like what you're looking at is the area for the actual.
I cannot hear you very well. Is there any way you can speak in the microphone or closer to a microphone or?
Or should we get a mic here? Right? It's just look up. Look up.
Okay. When you write x times dx, it looks a bit to me like this is going to be the area for the Euclidean measure, not for the Liouville measure, because like otherwise it should be x dy for like coordinates that matches the Liouville measure. So can you confirm that it's not? That it's not the area?
Okay. Let me go back here. Just a picture. I'm looking here in this situation here at the, so we're not talking about this one, we're talking about, where is it? Where is it? Here, right? Yeah. So indeed you can take X as your Liouville-Brown motion. As I said, this is a local martingale. And so you can write down immediately this here, just drop the ends everywhere. There's no extra, so stochastic calculus will do it for you. There's no reference here to any Liouville measure. Liouville measure is a very subtle object. We need it to, so the answer is no, there's no reference here to Liouville measure. Is this your question?
So what you're constructing is really the say area delimited by the curve, but area with respect to the Euclidean metric.
That's correct. That is correct.
Okay, so let's thank the speaker again. Thank you, Peter.